You know those formulas you learn in physics class, right? The ones for combining resistors? Ever wonder if they actually hold up in the real world, outside the textbook? Well, today, that's exactly what we're going to find out. We're taking those rules and putting them to the test, moving from just theory on a page to a real, hands-on experiment.
So here's the game plan. First, we'll quickly go over the rules we're actually testing. Then, I'll introduce you to the special tool we'll be using for the job. After that, it's experiment time, one for series circuits and another for parallel. And finally, the moment of truth. We'll see if what we found in the lab matches what the books have been telling us all along.
And this really gets to the heart of what we're doing today. I mean, it's so easy to just accept a formula because, hey, it's in the textbook, right? But the amazing thing about science is we don't have to just take its word for it. We can actually check it for ourselves. So the big question is, how do we prove these rules are true? Well, let's find out.
Okay, first things first. Before we can put these laws on trial, we got to be crystal clear on what they are. So let's do a quick refresher on the two fundamental rules for combining resistors.
So we've got two main scenarios. Over on the left, you see the series combination, where resistors are just lined up, one after the other. The rule here is super simple. You just add their values up. On the right, we have the parallel combination. This is where the current has to split and go down different paths. The math's a little bit different, but the concept's the same. These are the two ideas we're about to put under the microscope.
Now, to run a proper test, you need the right instrument. So let's meet the star of our show today, the meter bridge. This thing is designed for exactly this kind of precise work. And here it is, the meter bridge. It's built around a 1 meter long wire, which is where it gets its name. See, on one side, we pop in a resistor with a value we already know. We'll call that R. And on the other side, we put our X. That's the unknown resistance from our circuit that we're trying to figure out. So, what's the magic behind this thing? It all comes down to something called the Wheatstone bridge principle. The easiest way to think about it is like an old-school balancing scale, but for electricity. When the ratios on both sides are perfectly matched, a little detector, called a galvanometer, reads 0. That's our goal. Find that balance point, because that's the key to everything.
All right, it is officially experiment time. First up, we're testing the law for resistors connected in series. Let's see how it holds up. Okay, take a look at this setup. In that gap on the right, we've connected our two resistors, R1 and R2, end to end. That's our series connection. Now, as far as the meter bridge is concerned, it just sees that whole combination as one single unknown resistance that we need to measure.
The actual process is pretty straightforward. We pick a known resistance, R, from our box. Then we take this little sliding contact, it's called a jockey, and we just slide it along the wire. We're hunting for that one exact spot where our detector needle doesn't move at all. It reads 0. Once we find that sweet spot, we measure the length L, and believe it or not, that's all the data we need to do our calculation.
And here is the data we collected. Now, to make sure we're being accurate, we didn't just do it once. We took 3 separate readings using different known resistances. After we ran the numbers for each one, we took the average, and our experimental resistance came out to 2.72 ohms. Now, burn that number into your brain. Okay, on to part 2 of our investigation. We're going to check out that second rule, the one for parallel circuits.
You'll notice the circuit looks a little different now. We're using the exact same 2 resistors as before, but this time they're connected in parallel. That means the electric current gets to a fork in the road and has to split, with some going through each resistor at the same time.
We've followed the exact same procedure. You know the drill. Take 3 readings, find the average to make sure we're accurate. And this time, our data points to a mean experimental value of 0.66 ohms for the parallel setup.
Okay, deep breaths, everyone. We've got our experimental results. Now for the most important question of all. How do our real-world numbers stack up against the textbook formulas? This is it, the moment of truth.
Let's start with that series circuit. Remember the number I told you to keep in mind? Our experiment measured a total resistance of 2.72 ohms.
So what does the textbook formula predict? When we plug in the numbers and calculate it, we get 2.75 ohms. Wow, that is ridiculously close.
Okay, now for the parallel circuit, our experiment gave us a value of 0.66 ohms.
And the theory? The formula predicts a value of 0.68 ohms. Look at that. Again, it's an almost perfect match. So what about those tiny little differences? That, my friends, is what we call experimental error. No measurement in the real world is ever 100% perfect. It could be a tiny imperfection in the wire, or maybe how we read the scale.
But because our results are so incredibly close to the theory, we can say with total confidence, the laws have been verified. They work.
So, what's the big takeaway here? Well, first and foremost, those formulas in your physics textbook, they aren't just abstract ideas. They are real, testable descriptions of how our universe actually works. Second, we saw that a pretty simple tool like the meter bridge is powerful enough to prove these fundamental principles with amazing accuracy. The bottom line, our experiment was a total success. The laws of resistance hold true.
And that kind of leads us to one last, bigger question. We just proved a fundamental law of physics with a relatively simple piece of lab equipment. It really makes you wonder, what other principles, what other things we just take for granted are just waiting out there for us to test for ourselves, which is a little bit of curiosity and the right experiment.